Hello, this video is designed to improve our knowledge on the connection of resistors in electric circuits. So in this circuit, as that is displayed in this example, we have 9 plus 3 resistors labeled R1 to R9 and RA to RC. Six, 7, 8, 9 are also in parallel, and resistors RB, RC are in series, and both of them, RB and RC, are in parallel with RA. So, to determine the current flow out of the battery, it is important to start by determining the total resistance in the circuit. So that means that this entire circuit can be replaced with a single resistor. We can replace it with a circuit that looks just like this. I will say this is our 12 volts battery connected to a resistor. There is a particular resistor having a certain value such that when we call that R total, its value will be equivalent to all the 12 resistors combined. So let's start by trying to simplify this circuit. And a simple way to do that is to replace R1 and R2, which appear to be in series, with a single resistor, and RB and RC, which are also in series with a single resistor. So R1 plus R2 is in series the total resistance is straightforward. That is 6 ohms. So we should remember that our R12 is used to represent the total resistance of R1 plus R2. Similarly, RB and RC, sorry, this should be, let me take this out. RBC should be plus 3 ohms, and that is equal to 4 ohms. So that means we can replace these two resistors. Get another color with a single resistor rated at 6 ohms. We can also replace these two resistors with a single resistor rated at 4 ohms. Let's move forward. So we can see on this screen, RBC has been replaced with a single resistor, while R12, which replaces resistors R1 and R2, and resistor RB and RC. Now, we have resistor R4 and R5. We have RCA and RBC. So to replace R3, R4, and R5 with a single resistor, we need to treat them as in parallel, which is to say that since R4 and R5 are 4, 6, (1/4) plus 1 over 6, 1 over 2.4. Plus 1 over 6 plus 2.4 is 2 whole number that's as good as saying 1 over 2.4 is 5 over 12. So LCM, okay, it's 12. 12. Then we have 3 plus 2 plus 1. That's equal to 6 over 12. So 1 over R345 is equal to 6 over 12, meaning that R345 will turn it upside down. Or we'll find the reciprocal of both sides to have our R345 to be equal to 12 over 6 ohms. And that's equal to 2 ohms. So that means that we can replace the 3 resistors R3, R4, and R5 with a 2 ohm resistor. So now we are to resolve R6, R7, R8, and R9 in parallel. And the resistances are 6, 2, 3, and 4. That is 1 over 6, 2, 3, and 4. Let me confirm that 6, 2, 3, 4. Good. So then the LCM. LCM should be 12. This is 2, 6, 4, 3. And that is equal to 15 over 12. 15 over 12 can be simplified as 5 over 4. So since 1 over R6, 7, 8, 9 equal to, since 1 over R, let me, 1 over R6, 7, 8, 9 equal to 5 over 4. Then R6, 7, 8, 9 will be finding the inverse of both sides, and that will be 4 over 5. And that is ohm, and that will be as good as 0.8 ohm. And finally, RA and RBC, which are also in parallel. RA is 4 ohms, RBC is also 4 ohms. So that is 1 over 4 plus 1 over 4. For simplicity, let's follow suit and see LCM. Then the inverse of both sides will give us RABC, which is equal to 2 ohms. I'd like you to note that when we resolved R3, R4, and R5 in parallel, we obtained 2 ohms. The 2 ohms we obtained is even less than the least amongst R3 to R5. Similarly, when we resolved R6 to R9, we obtained 0.8 ohm, which is even smaller than the smallest among these 4 resistors. And also, when we resolved RA and RBC, which are both 4 ohms, we got a value which is half of the resistance value of each of them. So that means that when we have resistors in parallel, the equivalent resistance is smaller than the smallest amongst the resistors in parallel. Let me take that again. When we have resistors in parallel, their equivalent resistance is less than the smallest amongst the resistors in parallel. So now we have R345 to be 2 ohms, R6789 to be 0.8 ohms, and RABC to be 2 ohms. That means our original circuit, which transformed to, okay, let me hide this. That means our original circuit, which reduced to this figure, as we now have this form, where we have a single resistor to replace R1 and R2, another single resistor to replace R3, R4, and R5, a single resistor to replace R6, R7, R8, and R9, and a single resistor to replace RA, RB, and RC. So then, since we can see that the 4 equivalent resistors are also in series with each other, we can find their equivalent resistance as well. And that will mean R12, 6 ohm, plus R345, 1.2 ohm, plus R789, R6789, 0.8 ohms, and RABC, 2 ohms. And that will add up to 10 ohms. That means the original circuit we had can be replaced with this circuit. The entire resistors can be replaced with a single resistor rated at 10 ohms. So the original question is that what is the current flow out of the circuit? What is the current flow out of the battery rather? What is the current flow out of the battery? And to determine the current flow out of the battery, we use Ohm's law. From Ohm's law, we can obtain I by dividing both sides by R total. And from that, we have our battery to be 12 volts and the total resistance to be 10 ohm. And that will give us 1.2 ampere. So this is the total current that will flow out of the battery. 1.2 ampere is the current that will flow out of the battery. So before we leave, let us know that from this original circuit, 1.2 ampere will flow out of this battery, and 1.2 ampere will flow back to this part. 1.2 ampere will flow through resistor R1. 1.2 ampere will flow through resistor R2. But when 1.2 ampere gets to this junction, it splits into 3. The large fraction of the 1.2 ampere will flow through the smaller resistor, while the least fraction of the 1.2 ampere will flow through the R4 resistor, which has the largest resistance value. The three currents that have the current that are split into 3 will reunite at this point, and the value of the current that will flow through this line will still be 1.2 ampere. And that is what Kirchhoff's law has told us, that the current will flow to this junction, split into 3. That will mean that the current that is flowing into this junction is equal to the current that will flow out. And the current that will flow into this junction also will be equal to the current that will flow out, which will be the summation of the currents in the 3 branches, which will add up to 1.2 amperes. And the 1.2 amperes will get to this junction and split into 4 different parts. The larger chunk will flow through the least resistor, which is R7, because it is 2 ohms, and the smallest currents will flow through R6, which has the largest resistance value. In short, 1.2 amperes will split into 4 different channels, and they will come back here to still add up to 1.2 ampere. On getting to this junction, the current will split into 2. And at this point, we should, without any form of confusion, we should know that the 1.2 ampere will split into 2 equal halves, meaning that, because the reason why I can say that is because the total resistance on this top channel is 4 ohms, while the total resistance right here is also 4 ohms. So 1.2 amperes will split into 2 equal halves. So at this channel, we'll have 0.6 ampere. And okay, let me try to erase this one to say. At this point, we have 1.2 ampere, but through this channel, we have 0.6 ampere, and also through this channel, we have 0.6 ampere. So 0.6 ampere will flow through this. 0.6 ampere will flow through this 1 ohm resistor and this 3 ohm resistor, and they will reunite at this junction, and they will both add up to ampere. So I hope I've added some more information to just resolving resistors in series and parallel. See you at the next video.